Hi guys, welcome back. So in this video, we're gonna continue from our previous example, okay? And we're gonna model the DC motor with the integrators, okay? So if you guys remember from the example that we solved in the class, what we had was two integrators, okay, and the output of the first integrator was the current, and the output of the second integrator was the angular velocity, okay. So just for our reference, I'm gonna copy and paste um, this screenshot, okay, in my code, so I can refer to it during the simulations, okay. So let me just copy, okay, get the screenshot, okay, and then go to Simulink. And so I'm just going to start a new simulations, okay, a blank model here. And in this blank model, what I'm going to do is I'm going to just first copy the model that I had previously, okay, make it a little bit smaller. I could also go and make it fit to a screen, but for now, I think that is enough, okay. Now, I would go element by element, or block by block on this Simulink model. Okay, so I have a gain here with the value of 1 over L, an integrator again with the value of R, two gains also with the value of Km and Kb, another gain here, another integrator here, another gain here, one integrator here. Okay, so let's start from the where we left. Okay, so I'm going to bring a junction first. Okay, so if you guys remember, junctions were sum here, so I'm going to bring sum. Okay, and then another gain, so just bring a gain. Okay, and then another integrator, so I'm going to bring an integral. Okay, so integrator here is the integrator. Okay, and at last another gain here, gain, sorry, so this is another gain for Km. Okay, and if you guys remember, I do have one gain for R here as well. Okay, so what I'm going to do is I'm going to copy this gain, okay, and I'm going to paste it here. Okay, and also I would have another gain for 1 over J here, so I would have another gain here, copy it here. Okay, and also two gains in the smaller loop here and the bigger loop. Okay, so I'm gonna have this gain here and this gain here. Good. Okay, now with the gains I'm good. I'm gonna go after the summations. Okay, the junctions. I would need another junction for this guy, so I'll copy this one and paste it here. So for copying and pasting, by the way, I'm just using Control C and Control V in Windows. You can use Command C and Command V in Mac as well. Okay, so copy this one and paste it here. So at this point you're good. Okay, with the blocks. Okay, so just to make it a little bit nicer for myself to see, okay, I'm gonna have one scope also here for seeing the output of the system. Okay, so this is one scope, which is the output of the system. Okay, and probably I would need an input for this system as well. Okay, for this system, let's say that I'm gonna provide an input step. Okay, so I would have a step function here, and I'm just gonna bring it here. Good. Okay, now let's go and make these things a little bit nicer. Yes, so at the beginning you see that my junction here has En as positive, which is okay, but it also has Ri and Kb omega from the up and bottom, okay, from top and bottom with the negative sign. Yes, so I would basically click on this one. I would need divisions for this guy. Okay, so I would have positive and another division. Okay, divisions are just straight lines. Okay, and negative as well. Okay, so if you look at this right now, my junction is negative, positive, negative. Okay, so this is exactly what I wanted. Yes, then the gain here, the value for this one is not 1, it's 1 over L, so I'll just put it as 1 over L. Okay, and I click OK. The gain on the top, the value for this one is R. I'm just going to put it as R. Okay, and I'll just click it OK. Note that this gain should be flipped horizontally, so Control R or Command R. Yes, so with this, I was able to basically flip this one around. Yes. Now I'm going to go to the next gain, which is Km over here. Okay. I'm going to put the Km here as K sub M. Okay. And if you guys see, these values are already in my command, in my workspace. So I do not need to define them here. Okay. Now, I forgot to mention that I need the TL as well as a source from the environment. So let's bring TL again as a load torque. I'll bring it again as a constant. Okay, constant. This can be anything, any source. Okay, so the value 1 is okay. You can just keep it as it is. Again, in this junction, okay, you have negative on the top, positive and negative, and this is the output. Yes, so click on the junction again. Okay, so the same thing. Okay, negative divider, okay, and then positive, and then another divider, and then negative. Good. Okay, now look at this. Beautiful. Yeah, beautiful. So let's bring it here. The next gain is 1 over j. 1 over j. We're gonna bring the moment of inertia of the disk or the rotor. Okay, then I forgot to bring the integrator after this 1 over j. So this is the integrator. I just copy and paste it from the previous integrator. Okay, and at last here I would have a gain of b. So just double click on this one and put the value b over here. And this b is the bearing. Okay, so you just need to rotate this one horizontally or flip it horizontally, and at the end you need kb here. Okay, so kb is the value for the last gain. Okay, and we're gonna put it as kb. You see that the value of kb is the one that you have defined earlier, okay, in the system. Okay, and let's go ahead and flip this one horizontally as well. Okay, and you see that if you make these guys a little bit bigger, okay, you can see the values of the gains as well in them. Yes, so much nicer. Yeah. Okay, now let's go ahead and connect them together. Okay, so I'm going to connect the first one here, then this is the main line. Okay, which this one is connected to this one, holding control down or command down and clicking on the next button. Okay, so this is what I have here. Okay, and unfortunately this one is a little bit goofy, so I'm gonna bring it manually to the other one. Okay, and just click on them. Okay, the first one, the second one. Okay, and then also the last one. Okay, now if you guys remember, for getting the branches, we just right click and drag. Yes, so look at this. I need a branch for I here, which goes to R and then comes to the junction. Yes, so here is my I signal. I'm going to get a branch here. Okay, and I bring it to the gain, and from the gain to the junction. As easy as this. Yes, similarly, the output is omega. I would need a branch from omega and bring it to the value b. Okay, and bring it to the first junction, the second junction here. And similarly, I would need another branch. I would get it from here. This is omega. I'll bring it to the next gain, okay, which is kb. Okay, and then bring it to the second junction. Yes, okay. Note that the value of the signal here and here is the same. Yes, okay. And at last, I'm going to connect the T load to the junction here. Yes, okay. If you want to change the initial values for your current and for your angular velocity, you can go ahead and do that. Okay, I am happy with these initial conditions, so I'm going to keep them as it is. Okay, now let's go ahead and run the signal. Before you run the signal, let's bring another scope here for the value of I and the value of input as well. So this is your input step. Okay, input voltage, which is a step function. Okay, or en. Okay, input en, let's say. Okay, input e sub n. Okay, and this is basically the omega. Yes, so this is angular velocity, omega. Okay, and also you can get a scope for this one to see the input. So I would bring another scope here, and this scope is going to show me the input to the system. Okay, and I'm going to make it as my input value. Okay, and also uh, and also I would get another scope here for my current. Okay, and I would put this one as another scope here, and this is going to show the current value. Yes. Okay, so this is my current. Okay, so let's go ahead and run the simulation. You see that I run the simulations. This is ready now. Okay, it compiled the code, it ran the code, and now this is the value of your omega. Okay, which you see that the omega varies like this. Okay, and the value of the current is given to you as well like this. Okay, and if you want to see the input, you see that this is an input step, which the value of the input for the time before the step function, it's 0. Okay, and then at the step time it's gonna vary and come to the value of 1. Okay, so you can also adjust the value for this step. Right now this is a unit step with the step time at 1 second. Okay, so you can make it as 2 seconds, 3 seconds, or the final value, which is the basically the value of the step, you can make it 10, 20, doesn't matter. Yes, so they're all your choices. Okay, now one other thing that I wanted to show you guys is how to make this one a little bit nicer. Okay, I previously I told you that you can annotate these signals. Yes, so you can go ahead and annotate these signals with annotation. Yeah, there are other things that you can do. For instance, you can color code your code basically. Yes, so you can find blocks a little bit nicer. Yeah, so for instance, for this scopes, okay, I'm gonna right click on them. Okay, and I would go to basically properties. Okay, or block parameters. Okay, now let's go to properties. Okay, you see that on properties, you can define different properties for these scopes. Okay, and also you can go to format. Okay, and in the format you can change the background color of these guys, foreground colors of them. Okay, let's say I don't like the background color to be white for the scopes. I want them to be red. I want them to be green. Okay, so you put them as green here. Yes, and when you put them as green, you can assign all the green colors for your scopes. Okay, and for instance here you can bring the background color again for this one as green. Okay, and the background color for this one as green as well. Okay, so let's go here. The background color here should be green. Okay, and you can have that one as well. So I don't know what I changed here, that this scope is a little bit weird, so let me just get rid of it. Okay, and bring another scope. So another scope. Okay, and let's connect it here. Okay, and let's make the background of this guy also as green as well. Okay, so the background color for this one is green. Now eventually you are going to work with some code that the code has much more blocks than this one. Okay, so this is very simple example, and having color code for your blocks, for instance, all the integrators as red, all the scopes as green. Okay, it's going to help you down the way to identify and find them a little bit easier. Okay, so for instance, if I make an integral red, then I know that each integral is probably showing my states. Yes, so I would look at those integrals and find them a little bit easier in my code. So this is one thing. Another important criteria in Simulink is using what we call it as a subsystem. Okay. Now, what is a subsystem? Let's bring one of those subsystems here. Yes. A subsystem is basically a placeholder to just summarize your code and organize your code a little bit better. Okay. For instance, I can dump a portion of my code to a subsystem. okay, and use it eventually down the road. For instance, I can say that, okay, I would have a subsystem that calculates the probably the current. Yes. And if you double click on this subsystem, you see that you have an input which is connected to an output. Okay. And between this input and output, you can bring your code. For instance, look at this. I'm gonna say that, okay, I'm gonna bring this portion of my block to the subsystem. Yes. So this portion of the block is going to go to the subsystem, or let's say the other portion of the block. Okay. So let's see how I'll do that. Okay. So let me just get rid of this part. Okay. Now this is going to be a little bit uh, difficult, basically, because I need to dissect this. Okay. Junction in 484, we show you guys that you can actually break this one down to two junctions. Okay. But for now, what I'm going to do is I'm going to dump this value from here to here into this subsystem. So let me just copy and paste these guys. Okay. And I'm going to cut them. Okay. I'm going to cut them and I'm going to bring them to this subsystem. Good. Okay. I'm going to bring them to this subsystem. Okay. Now, look at this. Look at this. I can also bring the junction as well. Okay. So let's say that I'm going to bring the junction as well. Okay. So this is going to be the junction as well. Let's say that this is my junction. Okay. As well, which I brought it here. Yes. Now, for this problem, you see that because I wanted to bring this one to the subsystem, okay, and the subsystem comes here. Yes. So this is my current subsystem. And for this problem, to make it a little bit nicer and more organized, okay, you see that I would have two inputs that I cut them. One of them is the input en, okay, so I'm going to make one of these inputs as en. You see that? Okay, and this input is going to exactly come to the positive side of this guy. Okay, the other input, okay, would be basically kb omega. Yes, so this is my input 2. Yes, so I'm going to basically copy one of these ports and paste it here. Okay, sorry, just copy one of these guys, okay, and paste it here. For this one, I'm going to show it with kb multiplied by omega. Yes. Okay. Now, this kb omega, if it comes, it's gonna join here. Yes. And the output of this guy is basically kmi. Yes. So this is in fact my kmi. Yes. Which is the torque from the DC motor. Yes. So this is the torque from the DC motor. TM, basically. Yeah. And port number, sorry, I do not need to change the port number. I just need to change the name of this guy. Yes. So TM. So look at this. When you put this guy here, yes, then go back here. You see that you have two inputs here right now. The first input is en. It's really not difficult to connect these ones. Yes, en goes to en, and also km omega, sorry, kb omega, okay, which is your back electromotive voltage, comes here. Yes, so I can basically change this one, the name of this guy, to em, which is the back electromotive voltage. Okay, and at last it's going to give you TM, which TM comes and joins the junction over there. Yes, and you can bring everything a little bit down here right now, and this is how we use a subsystem. Okay, now the beauty of these subsystems is that if you have a huge number of basically portions in your code, or functions, or anything that that makes your code a little bit more complicated, you can divide them to different subsystems, okay, and then work on different subsystems separately. For instance, in this problem, I worked on the electrical subsystem, okay, and then this is the mechanical subsystem. I can do exact the same thing with the mechanical subsystem, okay. So this is the electrical domain model, okay, and also I can bring the exact the same or very similar subsystem for the mechanical domain. Yes, so let's go ahead and do that. Yeah, so I'm gonna bring a mechanical domain, sorry, subsystem, okay, and in this subsystem, very similar to what I had here, okay, I would have 3 inputs, okay, and these 3 inputs, let's copy these guys a little bit here, okay, so input 2 and input 3, okay, so they are the ports to my subsystem. The first one would be TL, which is the load from the environment. The next one is I could easily bring TL also in this subsystem, so I would not have it as an input. I'll show you guys how to do that, okay. Then the next one is T from the motor, okay, and the last one is, if you guys look at this, the last one is the T of the bearing, the torque from the bearing. Yes, so this comes exactly from your free body diagram, okay, directly from your free body diagram. So T of the bearing, yeah, okay, and then the output of this subsystem is just simply your omega. Yes, okay. Now look at this. In this subsystem, I'm gonna just bring. Let's get rid of this guy and this guy, okay, and also this guy, okay, and let me just bring all of these guys to here. Yes, so let's bring all of these guys to here, okay, and this is gonna be your output omega, okay, which I'm gonna get rid of this one as well, okay. This is your TL, comes here. This is your TM, comes here, okay, the torque of the motor. This is your TB, okay, or you can just instead of this TB, okay, you can just have it as such a thing, okay. So because you can get TB from omega multiplied by B, okay, you can just make it here, okay. Now let's go back to the model, okay. You see that right now you have TL and TM as the input of this subsystem, okay. You do not need the junction anymore, you do not need this one anymore, okay. And okay, let me just double check. And the integrator, you do not need it, okay. So you bring the subsystem here, okay, and in this subsystem, TL is going to be connected to TM, okay, and the load torque is going to go to TL, okay. Now omega is the output of this guy, will go to the junction here. Yes, okay, and at last you can get rid of the last one, the feedback loop, okay. So this is the mechanical side, okay, and you see that this is your mechanical domain, okay. Now this is exactly what we had in the class. Yes, so we had mechanical side and the electrical side. This is your electrical side, this is your mechanical side, okay. And there are variations that you can do, okay. For instance, instead of having KB over here, you can bring KB inside this guy, okay, and instead of having EM as the input of this subsystem, you can have omega directly, okay. And let me just bring this one here, so KB connects to here, and when omega comes here, okay, just pass it through KB before going to the summer. Yes, so you just pass omega through KB, and it goes to the summer. This is in fact gonna be kb omega, which is your back electromotive voltage. Okay, and like the modelings that we did in the class, okay, or in the videos that we have right now, you see that the input to the electrical side is En. Okay, also you need omega from the mechanical side. Okay, the input to the mechanical side are TL and TM. Okay, which TM is in fact KMI, which comes from the electrical side. Okay, and inside this mechanical system, you notice that you need omega to calculate the torques. Okay, for the bearing, as well as this omega will be used to calculate the back electromotive voltage in the electrical system. Just to make sure that everything is working, okay, I'm just gonna go ahead and run this. Okay, you see that the code's run without any problems. It's ready. If you look at the omega of the output of the system, this is exactly the same thing that we had before. Okay, so I hope you guys enjoy this. The subsystems are gonna be the ones that are gonna somehow make your life much easier in modeling with Simulink. Okay, so in the next video, I'm gonna talk a little bit about how you can use MATLAB Coder to basically solve some of these systems, and also I'm going to show you guys how you can actually use Simulink to use state space and state space representation to model your system. Thank you.